chemical equations are things that chemists use to describe a chemical change. It's like a recipe. It's telling you like what you have in the beginning and then what you're forming after a chemical change happens. So it's showing you your reactants, which is the substances that you have in the beginning, and then your product. In this case, we have only one product and two reactants, but we can have one reactant, two products, or two reactants and two products. Okay? We use an arrow to separate what we have in the beginning and what we have at the end. Okay? It's your reactants are always on the left side of that arrow, and then your products always on the right side of the arrow. So this represents a chemical change because it's showing you that you're forming a new substance here. Things that you should notice in your chemical equation. You have the same type of atoms in both sides of your equation. You have carbon and you have oxygen. You have carbon and you have oxygen, but you have them arranged in a new substance. On the left side, for this specific one, you have your element carbon, you have your diatomic molecule for oxygen, which is another element, and then on your product side, you have your compound, your covalent compound between carbon and oxygen, okay, forming carbon dioxide. Now, in your chemical equations, besides having your reactants on the left side of the arrow and your products on the right side of the arrow, you might have things indicating the physical state of your substances. For example, that S in parentheses right there means that that carbon, it's in a solid state. This oxygen is in a gas state, and then carbon dioxide here in a gas state. But we also use L for liquids. And when you have a substance dissolved in water, we're preparing a solution, and since we're using water to dissolve the substance, then it will be an aqueous solution. And to indicate that physical state, we use AQ. Besides indicating the physical state, we have numbers in a chemical equation. You have a number in front of your substances. Sometimes, if you don't have a number, it's because it's 1 and we don't write it down. But that number that I have here in front of carbon, in front of the oxygen, in front of carbon dioxide, it's a coefficient. And then you have, of course, the numbers that you already know, your subscripts, right, which are part of your formula, which are telling you how many of that specific atom you have. You have carbon dioxide, 1 carbon because you don't have a subscript there, and then you have a 2 for your oxygen because you have 2 oxygens bonded to that carbon. So the coefficients in a chemical equation are very important for this next part. Your equations are balanced when you have the same amount of atoms for each specific element on your reactant and on your product side. What that means is that if you have 1 carbon on the reactant side, you need to have 1 carbon on the product side. Because we have the law of conservation of matter, which is telling us that matter cannot be created or destroyed. It can change form. So if you start with 1 atom of carbon, you need to show your atom of carbon at the end on your product side, because you're not destroying matter. You're just combining your elements here to get a new substance, but everything that you have on this side needs to appear on the right side, on your product side. So I'm giving you here a different equation, but it has the same descriptions as the previous one. You have your reactants on the left side, your products on the right side. You have numbers, you have your coefficients in front of, And you have your subscripts in your formulas indicating how many of each atom you have. Whenever you're counting your atoms to make sure that your reaction is balanced, or to balance a reaction that is not balanced, this is what you do. The coefficient, it's multiplied by your subscripts. So when you have CH4 here with a coefficient of 1, your carbon as a subscript equal to 1. So that will be 1 from your coefficient times 1, the subscript in your carbon. Coefficient is 1, and your subscript for carbon is 1. That's giving you a total of 1. Now for your hydrogen, you have hydrogen here, your coefficient in front of your CH4, and that coefficient applies to everything that it's after. That's the main difference between your coefficients and your subscripts. This subscript here belongs to the hydrogen in CH4. It has nothing to do with the carbon. Okay? It's telling you that you have 4 hydrogens in this compound. Now the coefficient changes everything that you have after it. Okay? So that coefficient changes the carbon and also the hydrogen. So coefficient is still 1, but now your subscript is different because for hydrogen you have a subscript equal to 4. So 1 times 4, that's giving you 4 hydrogens. And then we have oxygen here. Coefficient in front of your oxygen is 2, so that's 2. And then your subscript, it's a 2 for this one. And that's giving you a total of 4 oxygens. Now on your product side, I'm going to do the same thing. On your product side, in front of CO2, where you have the carbon, you have a coefficient equal to 1. And the subscript for that carbon, it's also 1. Now for hydrogen, I have hydrogen here. I have a coefficient in front of your water molecule that is equal to 2. So I'm going to write down my coefficient. And for the hydrogen, you have a subscript that is equal to 2. Now for oxygen, you have oxygen in CO2 and you have oxygen also in your water molecule. So you have oxygen in both products. Okay? So you're still going to do the same thing, coefficient times subscript for both of them, and then you're going to add them because you need the total number of that specific atom. Okay? So the total number I'm going to do for the CO2 first. You have a coefficient equal to 1, a subscript equal to 2, and then for the water you have a coefficient equal to 2, and for your oxygen you have a subscript equal to 1. So 1 times 2 is 2, 2 times 1 is 2. So for your oxygen you have a total of, you're adding them, that's a total of 4. So I'm going to check my numbers, the total amount that I have on my product side and on my reactant side. If you have the same amount for each element, then your reaction is balanced. So for carbon I calculated 1, and on your product I calculated 1. For hydrogen it's 4, and on your product side it's 4. And then for your oxygen, on your reactant side you have oxygen, just the element, and you have a total of 4 atoms of oxygen. And then on your reactant side we calculated 2 in CO2, and then we have 1 oxygen in each water molecule here, which is another 2, giving you a total of 4 oxygen atoms, which is the same amount that you have on your reactant side. So this example here, it's a reaction that it's balanced because you have the same number, the same number of atoms for each element on your reactant and on your product side. But there are cases where that is not happening. And I need this that I have here. When a reaction is not balanced, okay, that your numbers are not the same, these are the things that you can and that you should not, you can do and that you should not do. Things that you can do. The only thing that you can do is change a coefficient. That's it. You can add a new coefficient to try to balance a reaction. If that coefficient didn't work, you can add another coefficient. Okay, you can change the one that you were using for a different one until you have a set of coefficients that will give you the same number of atoms for each element on the reactant and on the product side. That's it. You should not do any of these ones listed here. You will never change a subscript. The subscript is part of your formula. If you have here CO2, it's carbon dioxide. If you need to balance this equation and you erase that 2 for your carbon dioxide, you will get carbon monoxide, which is a different substance. You have carbon monoxide, different substance, different properties. Everything is different than carbon dioxide. So you cannot change a subscript because you will be changing the substance that you have. If you change your coefficient, you're not changing the substance that you have as a product or as a reactant. Your coefficient is just changing the number of each atom that you have for that specific substance. You are not going to add any substance. You're not going to delete anything from your equation. Things that you can do, changing your coefficients. Things that you should never do are these ones here. Changing the subscript, adding a substance, or deleting something that you already have. So there are no steps to follow to balance chemical equations. You should start with one element or one type of atom, and you can go from there. Just looking at the first one here, this is a simple chemical equation. You have just magnesium and oxygen. And just by looking at this one, you should notice that you have one magnesium, that's good. But you have 2 oxygens here, and you have only 1 oxygen atom in your formula for magnesium oxide. So this equation is not balanced because you don't have the same amount for each atom on your reactant and on your product side. So to balance your equation, you need to start adding coefficients, right? So if this is a 2 and you have only 1 here, I'm going to put a coefficient equal to 2 in front of my magnesium oxide. If I have a 2 here, that's giving me 2 magnesium atoms and 2 oxygen atoms. Now on my reactant side, I do have 2 oxygens, but I have only 1 magnesium. So when I change my coefficient here to get 2 oxygen atoms, I'm changing the number of magnesiums that I have, which means that now I need to change this coefficient here so I can have 2 magnesium, which is the same number of magnesium atoms that I have on my product side. You don't need to do anything here because that will be just 1, so you can write it down or you can just leave it blank. That means that you have 1 times 2, 2 oxygen atoms, and you have 2 times 1, 2 oxygen atoms. And you can check, you have to check, whenever you think you're done balancing your equation, you have to check that you have the same amounts. So I have here my magnesium and oxygen. Those are my two types of atoms. For magnesium, you have a coefficient that is equal to 2 and a subscript that is equal to 1. That gives you 2. For oxygen, you have a coefficient that is equal to 1 and a subscript that is equal to 2, and that gives you 2. Now, on your product side, you have a coefficient that is equal to 2 for magnesium and a subscript that is equal to 1, so that gives you 2 magnesiums. And then you have a coefficient in front of that is equal to 2 and a subscript that is equal to 1, and that gives you 2. 2 and 2, 2 and 2, your reaction is balanced. So I'm going to do the third one that I have listed here so you can see something. When you have polyatomic ions as part of your chemical equation, you can look at your polyatomic ion as a whole thing. In this chemical equation, just looking at your reactant side, you have your polyatomic ion sulfate and you have your polyatomic ion hydroxide. Now, when you check your product side, you still see your polyatomic ion sulfate here, but not the hydroxide. So I'm going to make a circle around the sulfate because that's the one that I have on my reactant and on my product side. If your polyatomic ion appears on both sides of your chemical equation, okay, you're going to look at your polyatomic ion as a unit. What that means is that when you're balancing this equation where you have your polyatomic ion on both sides of your arrow, you have one sulfate, one sulfate. You're not looking at this like I have one sulfur atom here and one here, and I have 4 oxygen atom here and 4 oxygens here. You're looking at this as I have one sulfate, the whole polyatomic ion on my reactant side, and one sulfate on my product side. That's simplifying the number of atoms that you're counting to balance your equation, because now instead of counting the S and the oxygen separately for this sulfate ion, you're just counting the ion as one. And now I'm going to move to check everything else. I have 2 hydrogens, but I have an additional hydrogen here. I have two sodiums and I have 1 sodium. So I'm going to start with that one because for hydrogen, you have hydrogen in 2 different compounds, but for sodium, you have it just in 1, okay? So that might be easier. You can do it in any way that you prefer. There's not just one way of doing this. So I'm going to put 2 here to balance my NAs. I have 2 NAs and I have 2 NAs on the product side. Now, when you're adding that 2 right there, you're changing your number of oxygens here. Now you have 2 oxygens and 2 hydrogens, right? 2 hydrogens here, and now you have 2 on this one because it's 2 times your subscript here, 1, that will give you 2 here. That's a total of 4 hydrogens, right? And in a water molecule, you have 2 hydrogens, but if you have 2 water molecules, that will give you 4 hydrogens. So you have 2 times 2. And then on your reactant side, you have 2 here and 2 here. That's 4. And on your product side, you have 4. So you have balanced your sodiums, your hydrogens, your sulfate. It's balanced because this is 1 and that is 1. Now you need to check your oxygens that are not part of your sulfate because you have oxygen here and you have oxygen here. 2 times 1 oxygen here, that's a total of 2 oxygens. And then you have 2 and your subscript here is 1, same as this one, subscript of 1, so that's 2 oxygens. So I'm going to break all of my elements here to count, and I'm going to keep my sulfate as it is. Coefficient of 1, coefficient of 1. Coefficient is 1 times 2. Then I have Na, it's coefficient of 2 times subscript 1. And then I have my oxygen, not the sulfate one, but this one, coefficient of 2 times subscript of 1. For my sulfate, I have coefficient of 1 in front of that one times just 1. And I'm missing here my hydrogen from the sodium hydroxide here, so a coefficient of 2 times subscript of 1, that's another 2. And then on the other side I have H, Na, O, and sulfate, same order. For hydrogen, I have hydrogen only in my water molecule. I have a coefficient of 2, a subscript of 2, that's 4. For Na, I have a coefficient of 1, a subscript of 2, that's 2. For oxygen, the one in my water molecule, coefficient of 2 times subscript of 1, that's 2. And for my sulfate, I have a coefficient of 1 times just 1 sulfate, that's 1. So this is a 2 here, that's a 2, this is 1. And for hydrogen, you have a total of 4. 2 plus 2 is 4, and you have 4. Na is 2, and you have 2. Oxygen is 2, and you have 2. And then for your sulfate polyatomic ion, you have 1 on each side of the reaction. Now I want to show you something else, and this is the last thing for now. This is my equation, and I'm going to write down my coefficients whenever they are equal to 1 to show you something. How we read this equation here: 1 mole of CH4 plus 2 moles of oxygen, when they are combined, you will get 1 mole of carbon dioxide and 2 moles of water. So this coefficient, it means that you have 1 mole of carbon dioxide, 2 moles of water, 2 moles of oxygen here, 1 mole of methane CH4 on your reactant side. That's what the coefficient is telling you. How many moles of each reactant you're mixing, how many moles of your products are you getting. So we can actually determine amount in grams. Amount in grams that you have for this reactant, for that product, and a total amount. So molar mass for CH4, and you can find this on your own using the periodic table. But molar mass for CH4, this is about 12. Each hydrogen is about 1. So when you add all of that, you're going to get a number that is close to 16, depending on your rounding. And molar mass unit is grams per mole. For O2, each oxygen is 16, but we have 2 of them, so that will give you 32 grams per mole. Now moving to your product side, you have here carbon dioxide. This is oxygen is 16, you have 2 of them, 32 plus 12 for carbon, that will be about 44 grams per mole. And then for the water, oxygen is 16, each hydrogen is 1, so you have 2 of them. That will give you a molar mass of 18 grams per mole. So you can find these numbers using the periodic table. Okay, molar mass for carbon plus molar mass for each hydrogen, molar mass for oxygen times 2 because you have 2 of them, molar mass of carbon plus your oxygens, that will give you this one, and then molar masses for your hydrogens, and you have 2 of them plus oxygen, that will give you 80. Now this is coefficient here. It means that you have 1 mole of CH4, and your coefficient is multiplied by that, right? That's plus, and here you have 2 mole of oxygen times your 32 grams per mole. Your arrow, this is 1 mole of carbon dioxide, and that's the mass, and that's your plus 2 moles of the water. That's that. So now I'm going to calculate like a total amount for your CH4, for your oxygen, for your carbon dioxide, and for your water. Units: 1 mole cancels with 1 mole, mole with mole, mole with mole. This is that number, this is this, and that's that one. So if you add together your 16 plus 64, that's a total of, on your reactant side, you have 16 grams for CH4 plus 64 grams for your oxygen. And I'm adding that, and I get 80 grams. On your product side, I'm adding 44 plus 36 law of conservation of matter. Okay. You can see this law based on the number of atoms that you have for each specific element on your reactant and on your product side, but you can also see by the total amount that you have. If you have 80 grams, right, on your reactant side, whenever you get your products, whatever it is that you're getting, the masses of your products, they need to add to the same mass that you had in the beginning, because you're not creating matter out of nothing. You're not destroying matter. Okay? Your atoms, carbon, hydrogen, and oxygen, they are recombining. Chemical bonds are being broken on your reactant side, and you're forming new chemical bonds on your product side to get your new products, okay, or the products of your chemical change. But the mass, it's being conserved. The total mass that you have on your reactant side is the total mass that you have on your product side.